Welcome, everyone. It's a great pleasure to introduce Joel Tropp, who is our speaker today for the Turkish Math Society's Distinguished Colloquium Series for February. Joel Tropp is Steele Family Professor of Applied and Computational Mathematics at Caltech. He earned his PhD at UT Austin in 2004, and after spending his postdoc at the University of Michigan, he joined Caltech in 2007. He has done some incredibly influential work on the intersection of probability theory, functional analysis, and numerical algorithms. His work has wide-ranging applications from signal processing and approximation theory to statistics and data science. He has many distinctions, such as the Picasso Award, the Vasil Popov Prize, the Monroe Martin Prize, as well as numerous Best Paper Awards and invited addresses. He's a fellow of the IEEE and the SIAM. He has been recognized as a highly cited researcher multiple times, and his papers have been cited in the tens of thousands. Today, Joel will be talking about universality laws for randomized dimension reduction. Again, thank you for accepting our invitation. The floor is yours.
Hi, Sinan. Thank you so much for the kind invitation to speak and the generous introduction. I wanted to say that I have actually a very large number of Turkish collaborators, and I wanted to highlight the work that I did with one of them, Samet Oymak, who got his doctorate at Caltech. He's a very talented electrical engineer who does a lot of work on applied mathematics and signal processing. And almost everything that I tell you today is really work that he is responsible for. So this is really Samet's project, and it's exciting to be able to talk to you about that. So with that, what is dimension reduction? So in words, dimension reduction is a way of taking a set, often in a linear space of some high dimension, and mapping it into a linear space of lower dimension in such a way that you preserve features of the geometry. So here's a little illustration. I've got some set T and Rn, and I think about mapping it down to Rd, which for simplicity I've embedded in Rn so that I can draw all of this on one picture. And the image of T in the lower dimensional space is phi of T. And the hope is that T may have some geometric features that are approximately preserved in the linear image in the lower dimensional space. So that's the goal of dimension reduction. It's a very simple idea. And it has applications all across applied mathematics and mathematical parts of engineering and computer science. So I got interested in this originally because of applications in signal processing, technologies for efficiently acquiring signals from a limited number of measurements, which is often called compressed sensing. And I'll highlight this application later in the talk. But there are actually a lot of other applications. So for example, in statistics, experimental designs are can really be viewed as a kind of dimension reduction. In coding theory, linear codes are actually dual to dimension reduction. The idea here is that you take some message and you make it longer in such a way that you preserve the structure of the message, and yet individual messages are now far apart from each other, so you can tell them apart. And it really is exactly dual to dimension reduction. And there are also a lot of applications I find interesting in numerical analysis. You can use randomized dimension reduction maps to build faster algorithms for linear algebra and for solving optimization problems. So there are a lot of things you can do with these tools, but there are also interesting mathematical questions about how they behave. And that's what I'd like to talk to you about today. But there are going to be a lot of pictures so that you can, really, I hope, get an idea about what's going on here. So we're going to look at maybe the simplest kind of dimension reduction problem. And the idea here is that we're going to be interested in a subset T in a high dimensional linear space Rn that has one geometric feature. It does not contain the origin. So this seems like perhaps a very trivial property, but nevertheless, this is really the thing that you need to understand in some applications, sets that do not contain the origin. Now, we'd like to take this high dimensional set and map it down to a lower dimensional space while preserving its geometry. Now, there's only one geometric feature that we've distinguished here, and that is the absence of the origin in the set. And we say that the dimension reduction map is successful if the origin is not in the linear image of the set. On the other hand, if after projecting the set down to lower dimensions, it now contains the origin, then you have failed. You've destroyed the one property that that set had that you wanted to keep. So that's sad. Now, we'd like to understand when it is that a dimension reduction map has this feature, that it keeps the origin outside of a set. And you may notice that this problem is scale invariant. It doesn't depend on how the magnitudes of the elements of T are distributed, for the reason that phi is linear. Okay, so since it's scale invariant, we may as well forget about the magnitudes of the elements of the set and pass to the spherical retraction, omega, by taking each of the non-zero points in the set T and pulling it back to the sphere. And now the success condition is exactly the same as before. For the spherical retraction of the original set T, the dimension reduction map succeeds if it doesn't map any of these points on the sphere to zero. And it fails if it happens to map one of the points in the set, the spherical retraction, to zero. Okay. So it's very simple. Now, here's a schematic of what we're doing here. So I've taken this set T, I've pulled it back to the sphere, and I've forgotten about the set T. And success for dimension reduction occurs when the projection onto the range does not contain the origin. So that's the picture that I've drawn here. So we map omega down to a lower dimensional space. It doesn't contain the origin. For simplicity, I've drawn all of this again in one diagram, and I've done that by introducing the orthogonal projector on Rn, whose null space is the same as the null space of the dimension reduction map. And so it's very easy to see that the only way that a linear map takes a point of omega to zero is if the null space of that map intersects the set omega. So that's the failure condition here. So if the null space of the dimension reduction map passes through omega, then some point gets dropped onto zero, and we fail in preserving that one feature of the geometry, that the set did not contain zero. On the other hand, if the null space of the dimension reduction map misses omega, then we succeed. And so we have this precise geometric characterization of when the dimension reduction succeeds in a geometric sense. So does the null space of the dimension reduction map hit the set, in which case we fail, or does it miss the set, in which case we succeed? Now, in most applications, you don't know in advance exactly what the set omega is. You might know something about it. We'll talk more about that later, but you don't know typically the precise set in advance. And as a consequence, you still want to build a dimension reduction map that avoids this unknown set. And so one way you might do that is by selecting a dimension reduction map at random, so that its null space is a random subspace of the space Rn. And so now you can think about the null space as spinning around. And then the question is, what is the probability that that null space of the dimension reduction map, which is random, what is the probability that that random subspace misses the set omega? That's success. Or what is the probability that the random null space of the random dimension reduction map hits the set omega. That's the failure condition. And so you can see the probability will help us in building a dimension reduction map that works for an arbitrary unknown set. And we'd like to understand the probability of success or failure for particular types of sets. Okay, so I think it's pretty easy to see what's happening here. So let's turn to an example. Now, the most natural thing you might do is draw a dimension reduction map whose null space is a uniformly random subspace of Rn with codimension d. So that the ranges has dimension d, the null space has codimension d. And in this case, you can actually build a very precise analysis of how these dimension reduction maps with uniformly random null spaces work when they succeed or fail. And I've drawn you one particular example that has a particularly simple description. So I've considered the probability simplex in Rn. So these are non-negative vectors whose entries add up to 1. So this is clearly a set of points that doesn't contain the origin. And I'd like to know when a random subspace of codimension d hits this set or misses it. Equivalently, what's the probability that a random subspace shares array with the non-negative orthant? So these are all equivalent ways of framing this question. Now, for this particular set, the analysis is actually quite classical. It goes back to work of Schläfli and Santolo, Wendell, Cover, Efron in different communities. And you can write down very precise formulas for the probability. And I've charted that here. So when the null space is big, it's very likely to hit the non-negative orthant, to hit the probability simplex. And that's true all the way up to a point around here where the probability starts to take off. And when the range of the dimension reduction map is larger, when the null space is smaller, it becomes very likely that it misses the set until the probability is essentially 1. Now, part of what's surprising about this picture, perhaps, is that the probability of success, the probability of preserving the fact that this set doesn't contain the origin after dimension reduction, surprisingly, this doesn't increase linearly. It's 0 for a long time and then jumps up from 0 to 1. Maurice has asked whether the distribution function changes when the dimension is large. The answer is yes. If you maintain the relative scale here, this will tend toward a step function. So the transition from failure to success becomes sharper and sharper. And this is maybe surprising because you might think that each additional dimension helps you out a little, but that's not true. If you don't have a big enough range for your dimension reduction map, you will fail. And as soon as the range of the dimension reduction map gets to be big enough, you will succeed. And the range of dimensions over which that character changes from success to failure is actually very narrow as compared with the dimension, and it becomes narrower as the dimension increases. Okay, so to recap, for uniformly random embeddings, we can compute exactly the probabilities for simple sets like the probability simplex, and for more complicated sets, there are at least theoretical tools for addressing this. But in practice, if you're actually using these dimension reduction maps for applications, it's actually not desirable maybe to use a uniformly random embedding in a lot of cases because even though they work very well and they admit precise analysis, they're hard to implement. I don't really want to dwell on the details. It's just that you can think about trying to draw a matrix that models that dimension reduction map. And although it's not hard to build a random matrix with a uniformly random null space, it does take storage and arithmetic to do that. And that may not be ideal for applications. So you might prefer some kind of structured dimension reduction matrix that has lots of 0 entries or has entries drawn from a discrete distribution like plus or minus 1, or has some other kinds of structure. So you can imagine that might be useful. So let me give you an idea about the kinds of things you might consider for applications, perhaps. So here is another dimension reduction map from a high dimensional space to a lower dimensional space that is both sparse and discrete. So most of the entries are 0, and the non-zero entries are drawn uniformly from the set plus minus 1. So these are pretty useful in practice. They're easier to construct, they're easier to store. Here's another sort of weird example, maybe not so useful, but it gives you some sense about the scope of these tools. The entries of this matrix are drawn uniform independently at random from a student T distribution with 5 degrees of freedom. So this has somewhat heavy tails, and you can see that one of the entries is actually significantly larger than the others. And so that's a feature of heavy tail distributions. And you might wonder whether this spiky kind of distribution behaves the same way for dimension reduction as a uniformly random, a matrix with a uniformly random null space. So that's a question. And you can do numerical experiments to interrogate this surmise. So here is a picture of that empirical probability, that theoretical probability of success curve for the reducing the dimension of the simplex. And here are empirical success probabilities for several different distributions for the random dimension reduction map. So the blue one is plus minus 1 uniform entries. These are called Rademacher random variables. Here's a sparse version of the same distribution, and here's that student T matrix. And what you see is that the success probabilities are essentially identical for all of these examples. So the success probability even does not seem to depend on the distribution, which is pretty interesting because these matrices don't really look very much alike. They have independent entries, but at the same time, these Rademacher matrices in particular are very sparse and have discrete entries, and the student T matrices are very spiky. They have some very, very large entries as compared with the sort of typical size of the entries. So we might like to understand what's going on in this picture. And that's the subject of the main result in this talk, is to argue that this is not an accident and that there is a deeper reason for this empirical result. So briefly, let me describe a model for random embeddings that we will be studying here. So we say that a random dimension reduction map from Rn to Rd is an independent random embedding when it has the following properties. We're going to assume that each entry is statistically independent in this D by N matrix. For simplicity, we're going to assume that each entry is standardized. So it has mean 0 and variance 1. So this is just a normalization condition to make sure that the entries are sort of on the same scale and they don't emphasize some dimension a lot more than others. We're going to assume that the entries have a symmetric distribution. So each entry of the random matrix has the same distribution as its negation. This is more technical. All the examples I've shown you have this property. It's not especially important, but it allows for the strongest results. And last, we're going to assume that each entry of the random matrix has bounded moments. So the fifth powers, say, are bounded in expectation. So this just ensures that the entries don't have very, very heavy tails. And some examples of matrices in this class include Gaussian random matrices, which indeed have uniformly random null spaces. Rademacher matrices, whose entries are uniformly drawn from the set plus minus 1. Similar sparse Rademacher matrices where we randomly delete, say, 90 or 95% of the entries. And also those student T matrices with 5 or more degrees of freedom. So there are a lot of examples in this class. It's a natural place to start studying universality properties, things that are true for a wide range of distributions. Much like the central limit theorem is true for any standardized sum of random variables that has a finite mean and variance. These kinds of results hold for any kind of random matrices with independent entries that have bounded moments. Okay, good. So these are the kinds of random matrices we'll be studying. And now the more interesting question is, how do we understand the characterization of the phase transition in these diagrams? So how big a dimension do we need if we want to preserve the geometry of a set? So it stands to reason that the bigger the set, the larger the embedding dimension that you need to preserve the geometry of that set. The smaller the set, the smaller dimension you can get away with. This is all very reasonable. And the question is how you measure the size of a set in this context. It turns out that the answer is quite elegant, but perhaps a little unfamiliar. So given a set T and Rn, we're going to define the statistical dimension of the set, which is a measure of its size, to be the following quantity. We're going to draw a Gaussian random vector with covariance identity. So each entry of this vector is mean 0, variance 1, Gaussian, independent. And we're going to take that random vector and we're going to project it onto the conical of the set T. And then we're going to compute the norm squared of that vector. And we're going to average that over all Gaussian vectors. Now, let's see what's going on geometrically and why it is that that might reflect the size of the set. So here is a convex cone K, which you can think about as the conical of this arc segment. Here's a random Gaussian. Here's the projection of the random Gaussian onto that cone. And you can see that it's pretty small. And so if you spin G around, the size of this vector will increase or decrease, but typically it's going to be relatively small in squared norm. And that will reflect the fact that this cone doesn't take up a lot of space. It's pretty easy to appreciate. On the other hand, if you have a bigger cone and you take a random Gaussian vector and project it onto that cone, you can see the projection is larger. And as you spin G around, it's often going to be the case that the projection of G is going to be a larger vector. And the average squared norm will be larger, which will reflect the fact that this is a bigger cone. It is the conical of a larger segment of arc. Okay. Any questions on this definition? Okay, so this is a very interesting geometric way to measure the size of a set, which we've retracted to the sphere. We might as well consider cones because everything's scale invariant, and we'll just ask how big a Gaussian is projected onto the cone. This is very closely connected with the mean width of a set, which is a basic concept in metric geometry. Now, what are some properties of this quantity? So first of all, it is monotone increasing with respect to set inclusion. So if E is a subset of T, then the statistical dimension of E is smaller than the statistical dimension of T. And that's not hard to see because the conical is getting bigger as the set increases. Moreover, this number is always between 0 and n. It's clear that it's always at least 0 because it's the average of a non-negative number. To see that it's never bigger than n, you can just observe that this projection decreases the norm of a Gaussian, and the squared norm of a Gaussian vector on average is the ambient dimension. So this has the right scale to be a dimensional quantity in Rn. And the reason we call it a dimension is that, and in fact, it reproduces the dimension of a subspace. And the reason for that is that if you project a Gaussian vector onto a subspace, you get a Gaussian on the subspace. And so the energy, squared energy in that Gaussian is simply the dimension of the subspace. This has some other beautiful properties. It interacts very nicely with polarity. So the dimension of the polar of a convex cone is the ambient dimension minus the dimension of the cone, which is a consequence of a result called Moreau's theorem. And moreover, which is not obvious, you can actually calculate delta t using analytical tools for a lot of interesting choices of the set T. And so one particular example, which actually already follows from what I've written on this slide, is that the probability simplex has statistical dimension n over 2 in n dimensions. The reason for that is that the cone generated by the probability simplex is the non-negative orthant. The non-negative orthant has a polar cone equal to the non-positive orthant. So those guys have the same dimension. And as a consequence, each one of them has to have half the total dimension as a statistical dimension. So it was pretty easy to see why this is true. So that's one particular example that is simple and beautiful, but there are other examples where that are more complicated, where we can also calculate this dimension explicitly. I'll show you another one later. Okay, good. So that's the statistical dimension, and this is the way that we're going to measure the size of a set for the purposes of dimension reduction, where our goal is to make sure that the origin stays out of the set after dimension reduction. And here's our main theorem. So again, this is Samet's work primarily. So assume that T is a compact subset of Rn that does not contain the origin. This is purely technical. The compactness assumption is not important. We're going to let phi be a random matrix drawn from that class that I showed you before. It's going to have independent entries that are standardized. And we have the following two claims. If the embedding dimension, the dimension onto which we squash the set, is at least the statistical dimension, then the random dimension reduction map succeeds with high probability. It keeps the origin out of the set. So this is the interesting direction. So this tells us that the statistical dimension really is a lower bound on the dimension that we need for dimension reduction of this type. So to keep the origin out of the set, we better project it onto a lower dimensional space whose dimension is at least a statistical dimension. So in the case of the non-negative orthant, you need to project onto at least half the ambient dimension if you want to make this work. There's also a converse, which is not always true. You need an additional assumption. So if the positive hull of the set is convex, so if you take all of the rays emanating from the origin through the points in T and you get a convex cone that way, then we can reverse this inequality. It turns out then in that case that if you want the dimension reduction map to preserve the geometry of the set with high probability, D cannot be any smaller than the statistical dimension. So you will fail with high probability if the embedding dimension is a little bit smaller than the ambient dimension. Okay, so at least for sets whose positive hull is a convex cone, the statistical dimension exactly characterizes the number of dimensions you need for embedding, the location of the phase transition, completely. Now, this error term here doesn't depend on anything except for some property of the random embedding class that we consider. This is true for every random embedding in this class. And the error term goes to 0 as the ambient dimension increases, which means that the phase transition gets tighter and tighter in higher dimensions. This term doesn't depend on the set that you're reducing. So for every subset of Rn, the statistical dimension captures the embedding dimension that you need to preserve the geometry of that set. So we already knew this for non-uniform embeddings before the work that Samet and I did. Extending this from uniform random embeddings to non-uniform random embeddings turns out to be a nightmare. This is not a book proof. The basic ideas involved are Gaussian comparison theorems and the Lindeberg exchange principle. Unfortunately, the full argument runs to about 50 or 60 pages. So I'm going to spare you any further details. It would be nice if we understood this a bit better than we do. But I can illustrate this for you, and that's what I'd like to do for the rest of the talk. So any questions on the statement of the result? Yeah, so that's a great question. So at least in the uniform case, there's some reason to believe that the probability, actually it's been shown that the probability distribution converges to the cumulative distribution, that phase transition curve converges to the cumulative distribution function of a Gaussian random variable with an appropriate mean and variance. So that's work of Larry Goldstein, Ivan Nordin, and Giovanni Piccati. But in the case of the non-uniform distributions, we don't really know. Other questions? Okay. Now, the reason that this is actually a simplification is because we can actually compute the statistical dimension in a lot of interesting cases. And to emphasize what this theorem tells us, we have not shown that for these non-uniform dimension reduction maps that all of these curves overlay each other. But what we did show is that all of these curves must jump from 0 to 1 around the statistical dimension. And moreover, that the width of the phase transition tends to 0 as the ambient dimension increases. And we prove that for all of these examples. So we've shown that there really is a phase transition in the embedding dimension at the statistical dimension for all of the random embeddings in this class. And in particular for the, for the simplex, the statistical dimension is half the ambient dimension. So we'll always see the transition here in the same place halfway across the diagram. Yeah.
Sorry, here's a question. So how do you formulate the set T as you increase the ambient dimension? The set T, in a sense, cannot remain the same, right?
No.
So how should we understand? Yeah, you understood the question.
Great question. So this is a non-asymptotic theorem. This holds in every dimension. Okay, so the little o here is just telling us that I'm hiding constants from you that only depend on the parameters in the embedding, but nothing else. The parameters here don't depend on the set. So this is true for every set in every dimension. Now, there are ensembles of sets that you can define in every dimension, like the probability simplex. And for those, you can talk about the phase transition narrowing as the dimension increases. But in fact, this result remains true even in a particular dimension for a particular set. And it will tell you that the phase transition becomes very narrow for all sets in high enough dimension.
Okay,
make
thank
sense?
you.
Yeah, Great. So now what I'd like to do is talk about the compressed sensing problem, which is the motivating example for this kind of work, although I don't think that it is actually the most useful example. But that's a conversation for another day. So what is compressed sensing? So this is the problem of acquiring a sparse signal. So in other words, a vector with a lot of non-zero entries from a random projection of that vector. So here's the setup. We're going to let x natural be a vector in Rn that we don't know, but we do know that at most it has S non-zero entries, where S is small in comparison with the ambient dimension n. Now, what information do we have about x natural? We assume that we can apply a random matrix to it, phi. I've changed notation for some reason. Phi r, this should be d times n. And you observe d random measurements of the unknown vector x natural, which we call z. So z is a vector in D or Rm in the notation of this slide. And this is all we see. So we know the dimension reduction map and we know Z, but we don't know X natural aside from the fact that it's sparse. Now, a basic idea in this area of sparse signal processing that dates back to actually the mid-80s is to estimate the signal X natural by solving an optimization problem. So among all signals, all vectors X, whose measurements, whose embeddings are the same as the observed data Z, among all signals that have the right measurements, we find the one that has the minimum L1 norm, under the theory that the minimum L1 norm is a reasonable proxy for sparsity. The solution to this problem is X hat, some vector in Rn, and we say that we succeed if X hat is exactly equal to X natural. So we've precisely recovered the unknown vector by solving this optimization problem. So this is exactly a question about random dimension reduction, and I'll show how this fits into the framework that I've described in just a moment. Okay, so we want to capture a sparse vector from random measurements. This is a random dimension reduction problem, and we want to know when solving this optimization problem exactly recovers the unknown signal. So you can do numerical experiments to try and understand what's happening here. And what you see is almost no matter what random dimension reduction matrix you use, you see exactly the same picture. For a given sparsity level, number of non-zero entries, if you don't have enough measurements, you do not recover the signal. You do not recover the signal. And then all of a sudden, when the number of measurements gets to be big enough, you start recovering the signal with very high probability over the choice of the random dimension reduction map. And then you basically succeed all the time. And the number of measurements you need depends on the sparsity level. And what's striking is that no matter what random dimension reduction map you use, sparse Rademacher, student T, whatever, you see the same picture. And this is something that was observed going all the way back to the early 2000s. And it was kind of a mystery for a long time. So why is it that, first of all, you see a phase transition? So that was something that my group resolved in 2014 completely. There's also related work from other authors in the same time period. And why is it that the location of the phase transition seems to be universal? It doesn't seem to depend on the kind of dimension reduction map you use. Well, the reason is because of the universality theorem I showed you, which is really the first comprehensive explanation of this phenomenon. So here's why this is true. We can replace that L1 minimization problem by changing variables. So now the variable, instead of being the unknown, will be the unknown plus a perturbation, U. And when we change variables, the problem that we are solving becomes searching over all vectors, all perturbations to the signal that don't change the measurements. And among those perturbations, we're going to look for the one that has the minimum L1 norm. Okay, so this is a change of variables from the previous problem. We couldn't solve this in practice, but this is good for analysis. And so we see that among vectors in the null space of the dimension reduction map, we're going to see whether there is any vector that can change the L1 norm to make it smaller. So that would mean that the perturbation has to be in the descent cone of the L1 norm at the point X natural. So this cone here is the descent cone of the L1 norm. These are the directions we can perturb X natural to make the L1 norm smaller. And if there were any such direction that would make the L1 norm smaller, we can move in that direction and the solution of the optimization problem would not be X natural. So that's what's depicted here. So if there is a direction in the null space of phi, the measurement map, that takes us into the descent cone of the L1 norm at one of these corners, sparse vectors are at the corners of the L1 ball, then we fail. Conversely, if the null space of the dimension reduction map misses this descent cone, then there's no direction we can perturb the ground truth, X natural, to reduce the L1 norm. X natural is going to be the only solution to that optimization problem. So a zero perturbation, okay? So you can see now that this geometry is similar to what I showed you before. And to make this completely explicit, we take the descent cone of the L1 norm, we map it by retraction onto the sphere, and we need to know whether the null space of this map hits omega or misses omega. And this set omega depends on both the ambient dimension and the sparsity of the unknown vector. So the descent cone for a sparse vector only depends on the sparsity. Maybe not obvious. It only depends on the sparsity and the ambient dimension. And so for any sparse vector, the descent cone is the same. So has the same shape anyway. And so then the question is, can we compute the statistical dimension of the descent cone if we want to understand how many measurements we need to recover a sparse vector? So the answer is yes. This is a non-trivial calculation, which has a very long history in the convex geometry literature. This is the asymptotic expression as the number of the sparsity over the dimension goes to a fixed ratio. And the statistical dimensions here on the vertical axis. So as a function of the sparsity over the dimension, the proportionate sparsity, the statistical dimension has this limiting profile. Okay. And so this is a very, very good estimate for the statistical dimension of the set omega, the spherical retraction of the descent cone of the L1 norm, which is the geometric object we need to study to understand the compressed sensing problem. Okay. Now, if you overlay that curve onto the two pictures that I showed you before you, what you see is that theoretical curve exactly lines up with the observed phase transition. So the theory tells you, first of all, that that curve is the number of measurements that you need for a given sparsity if you wish to recover an unknown sparse signal from random measurements. So if the sparsity is 10, then you need about 30 measurements to recover this vector with high probability when we're in 64 dimensions. Okay. Now, what the theorem that I showed you establishes is that this picture will be the same regardless of the random measurement matrix you use, provided that it's drawn from that class that I showed you. So the theorem that I proved, or that I exhibited to you, shows that we should see exactly the same picture in both of these cases, and indeed you do. So that explains the mystery of why these curves are universal, whereas prior work had shown that this white curve is indeed the location of the phase transition for a uniformly random embedding. Okay. Any questions on this?
I have a question, Joel.
Yeah.
So we are, I am trying to see in these pictures the familiar relation where the number of measurements have to be in the order of S log n. And I'm not seeing it. So
yeah, you don't see that because that's the sort of the limiting result for sparsity S goes to 0.
Yes.
And so if you work out the asymptotics of this curve at S equals 0, you will see square root 2 S log n over S.
Okay.
There's an explicit expression for the curve. It's a little complicated, which is why I don't write it on the slides, but that's where you get the standard result.
Okay, thanks.
Great. More questions? So I think it's pretty cool that this geometric dimension reduction theory explains so precisely what's happening in this example and shows that it is indeed universal over all types of random measurements. And now let me give you a amusing illustration that this actually has predictive power in the world. So this is drawn from a paper by Jorgensen and Sidke from 2014. So they're researchers working on foundational signal processing techniques for magnetic resonance imaging. And what they did was to try and understand whether these phase transitions could be used to predict the amount of data that you need to recover medical images. So they took a sick walnut and put it in the MRI machine and scanned it. So this is indeed a slice of a walnut as measured through the MRI. The top row is the structure, which is a posterized version of the image. So it's basically just 3 levels. And in the second row, we've also got the texture where you start to see the depth information a little bit better. Now, this is not a sparse image, but if you take the gradient of this image, it does become sparse. So you can see that there are only pretty limited places where there are changes from one level to another. And they use the sparsity of the gradient and a related related optimization problem to connect these pictures with the theory I showed you before for sparse vectors. So the sparse gradient allows you to employ the theory for sparse vectors. And so you can see that for the structure, the sparsity is higher than for the texture, where the gradient is a little bit messier. Now, they took that picture I showed you before of the phase transition for sparse vectors, and they drew a vertical line to indicate the relative sparsity of the gradient for the structure, and another vertical line for the relative sparsity of the gradient of the texture. And they predicted how many measurements you would need to recover the structure and how many measurements you would need to recover the texture. So the idea is that this is maybe a model for a real MRI problem. This might allow you to get some prediction for how many measurements the MRI machine would need to take in it to recover real medical images. Now, here's what they found. As the number of measurements increases, you recover the structure better and better, but you don't do a great job until the number of measurements is sufficiently large, at which point you have a sharp transition from poor recovery to excellent recovery. And that's what you see here in this picture. And they use the theoretical predictions from this kind of result to argue that it should take about 70 measurements to recover the structure accurately. And indeed, they found that it was recovered accurately with 68 measurements. So a very, very close accord between the theory and the empirical result. For the texture, the gradient is less sparse. And they saw that as the number of views increase, you get a more steady reduction in the error. And it's not entirely clear when you fully recover the texture. But the theory predicts about 186 measurements for recovery of the texture. And you can see that that actually accords pretty well with an agreement between the recovery and the original walnut image of the text, the image of the texture of the walnut. And to make this illustration even clearer for the structure, remember, the theory predicts you need about 70 measurements to recover the structure. If you take 40 measurements, you do a sort of okay job, but things are pretty messy. So you're not getting some of these fine details here, especially here in this part in the heart of the nut meat. If you take 60 measurements, you're doing a pretty good job, but you can see that the errors are still pretty big. So these are the discrepancies between the truth and the recovered image. So at 40, the errors are pretty bad. At 60, the errors are still pretty visible, especially here in the middle. But by the time you have 68 measurements, the recovery is essentially perfect. There is essentially no error anywhere in the image. And so you can see that these theoretical results even maybe have some direct application in this use of compressed sensing for magnetic resonance imaging from a limited number of measurements. My interests run along different lines. there are a bunch of other applications of these ideas in signal processing, statistics, coding theory, numerical analysis, and in math, in stochastic geometry and random matrix theory. My main interest is in numerical analysis, using these kinds of tools to build better algorithms for randomized linear algebra and optimization, where you take a large linear algebra problem and you reduce its size randomly so that you can solve the problem more efficiently. And these same results apply in that setting. And there's even a conjectured application in neuroscience, where some researchers argue that the brain may actually perform dimension reduction, and that perhaps these kinds of results about random embedding explain the effectiveness of the brain at taking the complicated world around us and reducing it to a relatively limited amount of information. And with that, I will leave you with a list of papers that I've discussed by myself and by other authors. And the main thing that I talked about today was a paper with Samet on universality laws for randomized dimension reduction that appeared in Information and Inference in 2017. Thank you so much for your attention, and I'll be happy to hang around and answer questions if anything has provoked your curiosity. Thanks.
Well, thank you very much, Joel. So are there any questions?
We're actually right on time.
You are. So I do have a question regarding the universality.
Mm-hmm.
So of course it can be formulated in a number of ways, but I wonder if, now you didn't actually explain us, I know the proof is very involved, and but is it possible to imagine some kind of, if you consider all probability measures of interest to you, you define the class of random variables, and imagine, let's say, a probability measure on them. Can we think of this transition point as some kind of, is there some kind of concentration phenomenon going on there? Can we imagine it over the space of probability measures?
Well, so there are two things going on here. What you're actually seeing in this picture is a concentration phenomenon, but it's not for the random matrices, it's something else. So it turns out that all of this you can refer back to the uniform case. And in the uniform case, there's an exact characterization of where this phase transition is, which holds with equality. And it's expressed in terms of some geometric invariance of a set called intrinsic volumes. So these include the volume, the surface area, the mean width, and other things up to scaling. And you can actually write down the answer to the problem in terms of the what are called conic intrinsic volumes. Now, the conic intrinsic volumes are very hard to compute in general, except for simple sets like the simplex. But we proved that these intrinsic volumes actually concentrate around a specific number, which is the statistical dimension. And what you see in this picture, the reason there's a phase transition, is a reflection of the concentration. So you can think about this as being the integral of a spike. And the spike in that sequence of numbers occurs at the index, which agrees with the statistical dimension. So that's roughly the reason you see this transition. There is also a second kind of concentration, which comes just from the fact that this is the thing you want is a Lipschitz function of the data. And so more standard kinds of concentration tools allow you to argue that one random matrix is as good as any other random matrix. What you don't know from those concentration tools, however, is where the transition would take place for a given kind of random matrix. So the universality is what tells you that the transition takes place at the same position, regardless of what random matrix you use. So there are lots of kinds of concentration hiding here.
Okay, got it.
I have a layman question as somebody who doesn't work on this field. When you explain this, you put the success as being zero being in the image or not, but isn't it just a very simple thing compared to the entire geometry of T, or what you want to recover? So how you make this into like zero being in there or not? How do you get the images out of or geometry out of just one data, zero being there or not?
Yeah, so the reason is that for this whole class of signal processing problems, the question really is, does the null space of a random matrix hit a set or not? Which is really this question about whether the embedding preserves the property that zero is or is not in the set. That's actually the reason for this particular formulation of geometric reduction, a geometric dimension reduction, which is the simplest possible notion. Now, if you look at this first picture here, you might wonder, well, what about something fancier? So how far is this set away from the origin? So that's something that Samad and I studied as well, and we have detailed results for that I chose not to share. What you're asking about is more classical notions of dimension reduction, which ask how well is the internal geometry of points in the set preserved. You can also study those results or develop those results using these tools, but you usually only get a one-sided bound. So you can argue that the Euclidean distance between each pair of points in the set is approximately preserved by dimension reduction, provided that the embedding dimension is at least as big as the statistical dimension of something, which is not quite the same as the set. But you don't get the converse result, because in those settings, you lose the convexity that you need to get the both sides of the transition. You only get an estimate for the minimum embedding dimension that suffices.
Or do you ever rotate the shape or do this multiple times with certain symmetry of changing the shape?
Great question. So in the case of sparse vectors, you consider all sign permutations of the sparse vector, and each sign permutation of a sparse vector gives you a different descent cone, because each one corresponds to a different vertex of the low dimensional phase of the L1 ball. And what's interesting there is that all of those cones, the descent cones, are isometric to each other. So you really only have to make one calculation for a given sparsity. But you are using the fact that all of those cones are isometric in this application. Okay.
Thanks. Thank you.
I'm totally outside this field, but I listened with interest. Not that I understood everything, but molecular dynamics is an area where there's thousands and thousands of modes, but at the same time, maybe 5% of them participate in the real dynamics. I was intrigued by your title. That's why I came. Well, I'm totally outside this field. Is there a way one could select the modes that would determine the process? I mean, I wrote a paper maybe 15 years ago trying to find the best subspace, but without using any of the statistical stochastic methods. But this may be an area that many people would be interested in without knowing.
I think some of our colleagues actually do work on this. I think Mauro is interested in, Mauro Maggioni is related and interested in problems of this type using dimension reduction to study molecular dynamics. I think Massimo Fornacier has also done some work of this type. There are absolutely prospects for this. there are actually a lot of very useful applications of these ideas in numerical computation, which are harder to illustrate, which is part of the reason that compressed sensing is a nice thing to put in the talks, even if it's kind of useless. And whenever you see some kind of sparsity in a numerical setting, there is potentially an opportunity for dimension reduction, for sure. The details, depend on the application, but I think that some of our colleagues have explored those connections, and either I or Sinan could perhaps point you toward the researchers that work most closely on these problems.
I had the right idea, but didn't know the right method to reduce the dimensions.
These are new. I mean, these are very new ideas in these areas. Yeah. So great. Anything else?
Well, let's thank Joel one more time. What a great talk.
And thank you all for joining so late in the evening. I realize that many of you are, drawn away from your families to attend. So thank you.
Well, same.